Hey everybody. Today we're computing equations of regression lines in R. We're going to look at the built-in data set cars. You can see that set with the view command and get a little more information about it with the question mark command. Here we see we've got 50 entries. These are speeds and stopping distances for cars in the 1920s. So it's not exactly fresh data. Before we do any sort of linear regression on this, we should make sure that we actually have a linear relationship between these variables. Let's get a scatter plot. I'm going to do this using tidyverse, using the ggplot2 package. So I need to load that up, library parenthesis tidyverse. There we go. If you haven't already installed tidyverse, you should do so with install.packages parenthesis quote tidyverse. I just need a rough and ready plot here, so I'm going to use the qplot command. I want to put speed on the x-axis, that'll be the explanatory variable, and distance on the y-axis, that's the response variable. I want to explicitly let R know that I am working in the cars dataset and that I want a scatter plot, so geom equals point. There we go. We can see that there's at least a mostly linear relationship here, so it's not completely ridiculous to do a linear regression. While we're at it, let's go ahead and throw a regression line onto this graph with geom smooth. To make sure that it's a linear smoother, we need to do method equals quote lm. And while we're at it, let's go ahead and remove the standard error bar with se equals false. There we go, reasonable regression line. We'd now like to find the equation of that line. The basic command that we're going to use is lm. I think it's somewhat easy to remember since we've already seen lm in the geom smooth command, linear model. The basic syntax is starts out sort of like an equation, y is a function of x. So we're going to start by putting the response variable, in this case distance, then a tilde, so that y variable is related to or is explained by the thing that comes next. The explanatory variable in this case is speed. If we had multiple explanatory variables here, we could do plus and then put the next ones, put the other ones in. I'll talk about those in a future video on multiple linear regression. Next, we need to explicitly remind R that we are working in the cars dataset. When we hit return now, we're going to get the equation of the regression line in this form. It's going to tell us the y-intercept and the coefficient of the x coefficient in the regression equation. So in this case, the equation of the regression line would be y equals negative 17.579 plus 3.932 times x. Great. So there's a lot more that we can do with this linear model function, with this lm function. So let's go into some of the basics that are very helpful to know when you're starting out in R. We can take this lm command, take the result, and actually assign it its own variable name. So let's just pick the name model here. I'm going to be kind of generic here. And we can see here in the environment pane that we actually have a list of 12 things. We can get some more information about that object with the summary command. A lot of this is more sophisticated than we will need in this, this introduction right now. But right off the bat, you can see you've got a 5-number summary for the residuals. And you've got some potentially useful data here for statistical inference if we view this set as sample data from a larger population. We also get multiple R squared and adjusted R squared, as well as an F statistic. Taking that one step further, if we do, view model, if I can type view properly, we get a little bit more information about all that is contained within that model object. Coefficients we've already seen, residuals, effect, fitted values, rank, and so on. Much of this will be very interesting to us. We can access this information just as if this were a data frame. Model, $. Let's go with residuals. In this case, we're going to get a vector of length 50, the 50 residuals in order for all the 50 entries in this data set. If we like, we can add residuals as a column or variable to our original data set. So let's do that. let's say cars, dollar, how about residuals? So this is going to create a new column in that cars data set. And we want that column to consist of the residuals that we got from that model. Okay, let's take a quick look at this and see them. Just retype view cars. Again, I mistyped view. There we go. Let's do the same thing with the fitted values. These are the values that are predicted for all of these different speeds. So cars dollar predicted is going to be model dollar, in this case the syntax is fitted values. And let's see what that looks like. Fantastic. So if we like, we could do a residuals plot, putting speed on the x-axis, residuals on the y-axis. The last thing I want to do in this video is to use this model to actually get some predictions for speeds that are not contained in this data set. For example, what if we have a car from 1920 traveling at, say, 12.5 miles per hour? So we're going to use the predict function here. And this is another deep function that we could do a lot of different things with. I just want to get through the basic syntax right now. The first argument we need to pass predict is the name of the model that we've created. So in this case, model. The second argument needs to be a data frame, and it needs to have a column called speed. It has to have the same name as the explanatory variable in our model. So we don't have a data frame right now with the values, the speed values for which we'd like to predict distances. So we actually have to build one. The command that we're going to use here is data.frame, and now we just need to specify what we want our columns to be. Fortunately, we only need one column. We are absolutely required to call it speed. Again, the explanatory variable has to have the same name as the explanatory variable in our model. And let's just put in a few values into this data frame. Let's do, say, 12.5 and maybe 15.5. And while we're at it, let's actually pick one that is in the data set. Let's say 17. Great. So this is giving us predicted stopping distances for cars traveling at speeds 12.5, 15.5, and 17. For 17, you can see that the expected stopping distance is 49.27. That's exactly the same as we're seeing in this predicted value up here.